Hello, and welcome to a new lecture on Cantera. Today, we will be learning about chemical equilibrium and how to calculate it using Cantera. I'm sure you know about the concept of chemical equilibrium. You must have already come across in your combustion course. But all the hand calculations that you've done for chemical equilibrium today will be replaced by calculations on Cantera. So let's get started with it. So chemical equilibrium is a condition where there is no net change in the amounts of reactants or the products for a reversible reaction. And what that actually means is that the rate of the forward reaction is equal to the rate of backward reaction. And that is valid for a reversible reaction. So if A plus B goes on to make C and D, and this is a reversible reaction. Initially, there is only reactants A and B present, and there are no products C and D. And so only the forward reaction takes place. As the concentrations of products C and D build up, backward reaction starts as well. And slowly, as the concentrations increase for C and D, the backward reaction increases. And so there comes a point when the rate of forward reaction becomes equal to the rate of backward reaction. That is known as the point of chemical equilibrium. There is also a concept of adiabatic flame temperature associated with it, which is supposed to be the highest temperature that a combustion reaction system is able to achieve, because it happens in complete adiabatic conditions. So the system starts to react adiabatically and then goes to a peak where it equilibrates. And that peak is the highest temperature, which is also known as the adiabatic flame temperature. So today we will learn how to establish the point of chemical equilibrium in Cantera, and also how to look at the how to find the temperature and the composition of the mixture at that point. So let's start with Cantera. I'll start Spider. All right. So calculating the chemical equilibrium point in Cantera is really simple. It's really literally just one line. It's just one function called equilibrate, and the function is a part of the solutions class. So let's first go ahead and take a look at the help for for this function. Today I will not be writing any full script here, so we will just be typing some commands in the console and looking at the output. In the next lecture, you will calculate the lower heating value of a fuel, and that is when you will actually use this equilibrate function in a script, and you will know exactly how to write it in a script. But today we will just understand the basics of this function, so let's get started on that. First, let us import Cantera as CT. Now let's define the gas phase. Equals CT dot solution GRI 30 dot YAML. Sorry, I put in some wrong braces there. Gas equals CT dot solution GRI 30 dot, and I keep using GRI 30 dot YML because I mean that's a very common input data file. And again, and it has a lot of species and a lot of reactions that we will use in our normal calculations. Once in a while, there will be some calculation or some reactant system which will be, so some other data file will be needed for it, because it will have species or reactions that are not a part of the GRI system. And then we will see how to include the other data files as well. But today we'll just use GRI 30. All right, so now let's look at the help. gas dot equilibrate. All right. So this is all that comes up. It's a bit short actually. So it says that equilibrate is a method from the solutions class. It has several options as well. So XY, which is XY is here. And there are several other options as well. Actually, for our purpose, we will not use other options. It will mainly be the XY option that we have here. So XY are these two are these sets of two properties. So you can either have TP, TV, HP, SP, SV, or UV. What this means is that if you type in gas.equilibrate in parentheses, you write TP, that will mean that Cantera will keep the temperature and pressure of the system constant while calculating equilibrium. Similarly, if you have HP written for the option in place of XY, Cantera will keep the enthalpy and the pressure constant while calculating equilibrium. For adiabatic flame temperature calculations, you will always have HP option, because by definition in an adiabatic system, there will be no change in enthalpy. And so HP will be kept constant in that case. Then there are also these descriptions about, or rather mentions about the method of solution. So the way Cantera solves for equilibrium is very different from what you must have solved in your combustion course. So Cantera uses one of these methods as you specify. There's an element potential method, there's a Gibbs method, there's a VCS method. We will not go into the details of these methods and how do they work, because that is out of scope of this course. But you're free to explore, for example, like say Gibbs function. What that does is it minimizes the Gibbs free energy by solving for the mole fractions of different species in the system. Likewise, there's the element potential method. By default, Cantera always uses the element potential method. If that fails, then Cantera will go on to use a Gibbs method that is supposed to be more stable, more robust. Let's go ahead and define the composition of the system. We will say gas dot TPX equals 300. That's the temperature that we will set. 1 atmosphere pressure. So CT dot 1 ATM. So this is a sort of a keyword in Cantera that sets the pressure at 1 atmosphere. So instead of writing 101325 every time, you can just type this term. And then finally, let's put in some fuel and air in some random composition. So we will have, say, CH4, that's methane, 1 mole of that, and oxygen, let's write 2 moles of that. All right. Now, if you look at the composition of this gas at this point, it only has oxygen and methane. Then what we do is we just type gas dot equilibrate, and in the options we will give HP. Right? We hit enter. So internally, Cantera has already calculated the equilibrium point. So now if we take a look, so we had set the temperature of the system to be 300 Kelvin here, right? Now, if we take a look at the temperature after calculation of equilibrium, we just type gas.T. You see the temperature has risen from 300 Kelvin to 3052 Kelvin. This is the adiabatic flame temperature of this reacting system. Right, so we've held enthalpy and pressure constant. We've taken the system or the reacting system of methane and oxygen to equilibrium point, and just by typing gas.T or the temperature that the equilibrium has attained, this is what comes out. So this is the adiabatic flame temperature. Now, if you look at it, the composition would have changed as well. So now if I have to type, say, gas And if I say, earlier, we only had oxygen and methane. Now see, there are so many different species here. In addition to that, there are 34 additional minor species, which means that the concentration is so small of these species in this equilibrium system that it is almost negligible. And so Cantera has mentioned some of the biggest composition, some of the biggest species here in terms of concentration, in terms of mole fraction. So if we want to find, okay, when methane and oxygen combined in this ratio and attained an equilibrium, what is the final mole fraction of, say, carbon dioxide and water that was created? So all you do is, and we've discussed this before, you write gas dot x, which is for mole fraction, gas dot species index CO2, right? So this is the mole fraction of carbon dioxide in this system after it has reacted all the way to equilibrium. And you can probably match it from here as well. So here, see, 0.11278, that is the mole fraction. Now, if you want the mole fraction of water that was created, you just write H2O. Oh, that's hydrogen. Just write O here as well. And so this is about 40% of the products are water, and 11.2% by volume of products is carbon dioxide. So that's what this entire concept is on equilibrium, and it is extremely easy. Actually, Cantera makes your life very, very easy when it comes to combustion related calculations, as you've already seen. So if you had to calculate the adiabatic flame temperature and the composition at the equilibrium point, it would have taken you significant effort if you want to do it by hand. But by using Cantera, it's just one small line and you get everything out of it. So, well, that was all. And in the next lecture, we will see how to use this equilibrate function and perform bigger tasks and make more complex scripts. All right. Thank you so much.